Okay, so we've been talking about acids and bases. Obviously, previously we've talked about calculating pH, pOH, H plus concentrations, OH minus concentrations. So again, we had several formulas, obviously, that we use to do those things. We have our pH is equal to minus the log of our H plus. We also have our pOH, which is, again, a similar type of scale, but it obviously measures OH minus versus H plus. And again, the nice thing between sort of these two here, as we talked about, is, again, if pretty much if you add them together, you're going to get 14. So it gives you a little bit of options in terms of how to solve for certain things. We also obviously talked about KW, which is essentially a constant. For the most part, it really doesn't change numbers. The only time it would change numbers is, as we talked about, if it really wasn't 25 degrees Celsius, but most problems, do sort of stay at that 25 degrees Celsius. So this allows us to basically, calculate either the H plus or the OH minus concentration, depending on sort of which one is given to us. Is there a question? We're good. Yeah. Now, we can also, if we have the pH, as we talked about, calculate the H plus concentration from it by taking the inverse log of the minus pH. And that obviously is a 10 and a caret on your calculator when you do that. We also have the pOH, which allows us to get to the OH minus concentration, really the same calculation, just obviously using the pOH in that particular case. Then last time we started talking really about, how to calculate the pH of, say, weak acids and weak base type solutions. And to do these really do require ice tables. Again, the idea here is that they're weak acids, weak bases. They're really weak electrolytes, which means they are going to set up that equilibrium. And basically, we do it pretty much the exact same way as we've done other sort of equilibrium problems, ice table problems. The main difference, though, is we use a Ka value if it's a weak acid. And the only difference is when we do solve for X here, that usually will equal the H plus concentration, and that will allow you to go into the pH, obviously, to calculate it. We could do weak bases the same way. We use a Kb value, which obviously stands for base. And same thing, though, when we do the ice table, we solve for X. In this particular case, the X typically will equal the OH minus concentration, which does mean you got to do a couple of steps there. You got to probably first get the pOH and then get to the pH. So they're ultimately really just equilibrium problems. The main difference is we're usually interested in pH versus, say, in like a traditional equilibrium problem, like everybody's concentration at equilibrium. And we just kind of want to either get the H plus or the OH minus. We could treat them the exact same way as we've done equilibrium problems before, or you can do the quadratic if that's appropriate. You can obviously do a perfect square if that should work. You could do the assumption as well. A reminder, though, as we saw, I think last time as well, if you do the assumption, you want to make sure that you do check it because it will not always work. Any questions on that stuff that we talked about sort of last time? So I believe this is sort of where we left off, sort of talking about Ka values and Kb values specifically. And there's sometimes always an issue with students in terms of maybe they're not quite sure which one they should be using. And, it's a very common sort of problem that occurs. And again, the really sort of simple way to help you determine, should you be using a Ka value in this calculation? Should you be using a Kb value in this calculation? Is really based off of the equation. And that's why I think we talked about last time as well. It's really important to be able to write these equations correctly and really understand what you should be getting on the product side. Because when we look at an equation like this, we do see H plus here on the product side. We see H plus or H3O plus, which is pretty much the same thing. That should automatically kind of tell you it's an acid type situation. You should be using a Ka value. If you happen to write an equation and you end up with hydroxide there on the product side, that should tell you it's more of a base situation. And again, here, you should be using a Kb value. So that's a really good way to check yourself to make sure that you are really using the correct K value. As I mentioned last time, as we'll see today as well, there are certain problems where they will sort of give you the wrong K value. In a sense, they'll give you the Ka value when you need to actually use the Kb value, and vice versa. They'll give you the Kb value when you need to use the Ka value. So what does that mean? Well, it means there should be a way, obviously, to go from one to the other, the Ka to the Kb, or the Kb to the Ka value. And you can do that by actually adding these two reactions together. So we have like an acid reaction plus a base reaction. If we get rid of things that are the same on opposite sides of the arrow, what we're actually left with is basically water. And water obviously has its own equilibrium constant, which is Kw. So Kw is really the sort of bond between Ka and Kb. And this is a way in which we can go, relatively quickly from the Ka value to a Kb value and vice versa. Again, this Kw is that 1.0 times 10 to the minus 14 number. So we could use this very quickly to calculate either the Ka value or the Kb value that we may be interested in. And again, you will need to sort of use this in certain situations, but a lot of it does come with the proper recognition of what you're dealing with. And that again comes with being able to write these things, correctly. Again, I mentioned, I think last time as well, that, I've seen many times people go write reactions and they're not really sure how to do it. And they end up with the wrong thing on the other side. They end up with, for example, H plus on the product side, when they should not be getting H plus on the product side. They should be getting OH minus. And again, what that does is not necessarily just the equation is bad. It's going to send off your calculation in a bad direction as well. So they're very, very much sort of tied together. Any questions on that? All right, so before we kind of get into that stuff, let's talk a little bit about acid strength and sort of ways in which we can kind of compare acids and see sort of which one might be stronger or not. So the first type of acid that we're going to sort of look at here is a acid with really no oxygen. Whoops, try that again. No oxygen. So these are acids with no oxygens. These are like our hydrochloric acid, hydrofluoric acid, hydrobromic acid, and so forth. And because they do not contain oxygen, what we look at in terms of strength is actually bond energy. And that might be different than what you might think. You might think, well, we have a bond between, say, HF, or we have a bond between HCl. F is more electronegative, which means, again, the electron should be heading more this way and making this bond weaker. And you may think, well, that will make it a stronger acid. And actually, in this type of acid, without the oxygen involved, we actually don't look at electronegativity. We actually look at bond enthalpy, as sometimes referred to, or bond strength, sometimes referred to as bond enthalpy. You might remember that from bonding chapter. And what we see when we compare the bond between hydrogen and fluorine, chlorine, bromine, and iodide, this is basically going down group 7 on the periodic table. We see that the bond strength for HF is 565, and the bond strength, say, for HI is 295. What that means is it takes a lot more energy to try to break that HF bond than it does the HI bond. So a lot more energy to basically pop that bond apart. So what does that mean? Well, in comparison of the two, it means it doesn't take as much energy to break this bond, which means this guy's H plus should come off a lot easier. So what does that mean in terms of it being an acid? What does an acid really mean? An acid pretty much means the ability to produce H plus. So if this bond is easily broken compared to the HF bond, the HI is actually going to be a stronger acid than HF because harder to break the HF bond, which means the H is going to hang on there a lot longer. Not as much of it will come off, and it will be a weak acid versus HI. So when we think about acids that, again, do not contain oxygen, we're almost talking mainly or mostly group 7 here. It actually increases as you go down in group 7 in terms of acid strength. Again, these three are pretty much classified as a strong acid. And this guy here is our weak acid. So no oxygen comparing acids. We're looking at bond strength. And in group 7 acids, basically bond strength decreases as you go down, meaning that the H will come off easier as you go down in group 7. And that makes it a stronger acid. Any questions on that? Here's again a table as well that kind of describes that, and it kind of relates it to base strength as well. Again, this is the periodic table. Essentially going to the right and down, you get a much stronger acid, which is this guy's. Kind of going up and to the left, you can see you're getting a stronger base happening. So going up, and again, over there, you got a weak base, a very weak base with pH 3. But in terms of our acids, again, we kind of see the same thing. Weaker acid here, H2S versus HCl, again, is further to the left than HCl. So that kind of general trend for acids is kind of to the right and down, stronger acids on the periodic table, kind of up and to the left, stronger bases on the periodic table. And if you just think about, what you have kind of on like this side of the periodic table, which is up and to the right, you got like your sodium hydroxide, your potassium hydroxide, right, your calcium hydroxide, and so forth. So up and to the right on the periodic table, that's where we're going to find a lot of our strong bases, right, for sure. And that's where a lot of our alkali metals, right, alkaline earth metals are. And again, going the opposite way, a little bit weaker. Let's talk a little bit about acids, though, that actually do contain oxygen. These are sometimes referred to as oxyacids because, they contain oxygen. That makes sense. So oxyacids are guys that basically contain oxygen. And when we are analyzing sort of these type of acids, there's really two things we look at. One thing we may look at is, and it's always about sort of the center atom, if you will. We may look at the electronegativity of the center atom. A reminder, electronegativity up and to the right increases, right? Electronegativity. We may also look at the central atom's oxidation state and sort of use that to help us sort of compare acid to acid. So let's take a look at sort of one situation here. And this is a situation where we have a oxyacid with different central atoms, but are from the same group on the periodic table. So here the central atom is chlorine from group 7. Central atom here is Br, also from group 7 there. And they have the same oxidation numbers. So if we were to calculate oxidation numbers, as you might remember how to do that. If not, we will talk about it a little bit later on as well. But in general, assigning oxidation numbers, oxygen typically has an oxidation number of -2. So this oxygen would have an oxidation number of -2. This oxygen would also have an oxidation number of -2. This oxygen, surprisingly enough, also -2. Pretty much oxygen has an oxidation number of -2, except if it's peroxide, then it's -1. Hydrogen is +1. So when we add up all the oxidation numbers, it needs to equal the charge on the molecule, which the overall charge here is 0. So if we just add up all of our negatives, that's -2, -4, -6, +1 gives us a -5, which means the oxidation state, again, not the charge on chlorine here, but the oxidation state is actually +5 in this sort of arrangement with those three oxygens really attached to it. If we do the same thing for the HBrO3, again, -2 for this oxygen in terms of oxidation state, -2, -2, and +1. What we end up with is the exact same thing, -2, -4, -6, and +1 is -5. Oxidation state, again, not the charge, but the oxidation state here of bromine in this sort of arrangement is +5. So they do share basically the same oxidation number, which means we cannot use oxidation number to help us decide, which one is going to be sort of a stronger acid or not. So in this particular case, we would look at electronegativity. And in comparison of chlorine and bromine, chlorine is more electronegative. So what does that mean? Well, to start with, this is a polar bond, right? The hydrogen is more positive, the oxygen is more negative, just that OH part of it. And what that means is, for the most part, the electrons are kind of moving towards the oxygen in this bond, right? Now, because chlorine is more electronegative, it's going to kind of, if you want to think about it, move those electrons even closer sort of to the chlorine. Same thing sort of happening on this guy, positive and negative, again, moving in, but bromine is not as electronegative, so it's not going to pull those electrons as much on that side. What does that sort of pulling of electrons do? Well, if we think about sort of the bond between the H and the O, which is really what makes this an acid, as those electrons get pulled closer and closer towards the oxygen and then closer towards the chlorine, what you're essentially doing is taking this bond and making it weaker and weaker, this bond. And it's going to allow that H to come off a lot easier than this bond over here. You're also weakening it, but it's not as much as you are in this, in the case of the chlorine over here. What that means is, in terms of strength, we would expect that the HClO3 is a stronger acid than the HBr. Again, because of the greater electronegativity of chlorine versus bromine in this case, is going to kind of really pull those electrons in and ultimately weaken this bond more on the left here than it would on the right. And again, the whole idea of something being an acid is that ability to basically release or produce that H+ ion in solution. So in a case where you're comparing acids that contain oxygen and you basically calculate the oxidation state of the central atom, and it's the exact same number on both, what you then default to is electronegativity. Any questions on that? Okay. Now let's talk about sort of the other situation that could occur. And this is a situation where we have the same central atom, but we actually have different groups attached. And what we see here is, because there's actually different groups attached, unlike kind of here in this situation where to the central atom, we pretty much had everybody the same on the outside. The only difference was really the central atom. Here, the only difference is pretty much everything other than the central atom. We want to look at oxidation numbers as our goal as to figuring out which one's a stronger acid, which one's a weaker acid. So we would apply our oxidation numbers just like we did before. Oxygen, always a really good place to start, going to be -2. Hydrogen here going to be +1. +1 and -2 is -1, which means the oxidation number here of the chlorine is +1 in this situation. Coming over here, -2 for this oxygen, -2 for that oxygen is -4. +1 is -3. And again, that is how we get to +3 in terms of the chlorine in that guy. This is the guy we just did on the other page, -2, -2, -2, and +1, I'm sorry, gets us a +5. And then if we go to perchloric acid, we got -2s all the way around here for our oxygens. We got a +1 happening there. So -2 times 4 is -8, +1 is -7. That means that the chlorine in this particular molecule here carries a +7 charge. So what does that mean? Well, just like we sort of talked about with electronegativity, it is that OH bond that is really what needs to be broken in order for it to be an acid. So if we have that center atom that has a very big positive charge, we have that central atom with a big positive charge, it's going to bring those electrons, much like we just talked about with the electronegativity, in more and going to allow this bond to be broken a lot easier. The result of that is you will be ending up with a stronger acid here and a weaker acid here. Again, not as much of a pull on those electrons in that OH bond and the +1 versus the +3. Remember, strength of sort of positive, negative charges increases with the number. So the larger the number, the greater the kind of pull things have on each other. So if we were to arrange these in terms of strongest acid to weakest, this guy would be our strongest, and this acid here would be our weakest. So in a situation where we're comparing acids where we have the same central atom but different groups attached, we're looking at the oxidation number of the central atom. The greater the oxidation number, the stronger the acid it is. Again, a very simple sort of concept of electrons are negative, positive center, going to be pulling those electrons away from that OH bond and ultimately be weakening that bond, and again allowing it to obviously do its thing as an acid and pretty much donate it or get rid of it. Any questions on that there? Okay, so these are the ways that we can sort of compare acid strength, and again you kind of want to break them up based on sort of their properties, if you will, and what you should look at. So no oxygen, basically, you look at bond enthalpy or bond strength. Stronger the bond energy, the weaker the acid. If it does have oxygen and the same oxidation number in the central atom, you look at electronegativity. The higher the electronegativity, the stronger the acid. If they have the same central atom, but different groups attached, you look at oxidation number. Again, higher the oxidation number, stronger the acid. Any questions on any of that there? So the next thing we're going to talk about then is salts. And where do we get salts? So remember that in general, right, if you take an acid and you take a base, you basically produce two things. You produce water and a salt. So a salt really is just an ionic compound. It is usually produced as a result of an acid-base reaction occurring. So it is also sometimes a very good thing to think about it that way, because it helps you in the calculation part involving salts. It helps you decide, kind of what's going to happen with that particular salt based on where it came from. Now, there are some salts that are neutral salts, and this ties together with what we talked about earlier on in this chapter, and that's that relationship between an acid and its conjugate base, or a base and its conjugate acid. So if you remember, there's basically an opposite relationship, right? There's an opposite relationship between those two, which means if you started with a strong acid, its partner is going to be relatively weak. If you came from a weak acid, its partner will be relatively strong. And same thing with our bases. If you started with a strong base, its partner or conjugate partner will be relatively weak. And if you started from a weak base, its conjugate partner, like its conjugate acid, will be relatively strong. So there's that sort of opposite relationship that occurs between sort of the salt and where it came from. So what does that mean? Well, when we talk about it in the sense of the salt being strong or weak, what we're talking about is at some point, if the salt is sort of considered strong, it will have the ability to continue to react. And what is it going to react with? It's going to react with water. And depending on the salt, it may have the ability to produce H3O plus, or it may have the ability to produce hydroxide when it reacts with water. If the salt is weak, essentially what you will have is this right here. You'll have a neutral solution. There will be no reaction occurring. So, and the conjugate base of a strong acid like Cl minus, Br minus, NO3 minus. So if the salt comes from a strong acid or a strong base, the salt is going to be considered a neutral salt, which means it will not react with water and will not go through hydrolysis. What is hydrolysis? It's basically a reaction with water. So a neutral salt will not go through hydrolysis. The good thing about that is it's neutral, which means the pH of that solution should be 7. So we would expect, if we have just a salt, that the pH of that solution should be 7. Something like sodium chloride in water, right? If we think about basically the 2 parts of sodium chloride in an aqueous solution, that is, as it writes there, a sodium ion and a chloride ion. Now, when we have a salt, we will always have 2 parts. We will have the cation, the positive guy, and we will have the anion, the negative guy. Now, in a lot of cases, perhaps only one of these things will be strong and go through hydrolysis. It is possible that both of them could, and it is possible, like in this situation, that neither will. So why is thinking about sort of where the salt came from important? Well, if you think about where perhaps this salt was generated originally, you might be able to figure out that probably in most cases, it probably came from like the reaction of hydrochloric acid plus sodium hydroxide. That is going to give you water and sodium chloride. Right? So double displacement here. So HCl technically would be where the Cl minus came from originally. HCl is a strong acid, which means the Cl minus should be weak and will not go through hydrolysis. The sodium most likely came from sodium hydroxide. Is probably where that sodium ion came from. And since sodium hydroxide is essentially a strong base, the sodium part here of this salt will also be weak and will not go through hydrolysis. So that's why it says salts containing alkali metals and alkaline earth metals are going to be neutral. So if you remember our conversation last time, a lot of the strong acids are found in group 1 and a lot of the strong bases are found in group 1 and group 2 of the periodic table, things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and so forth. So if you see something that came from group 1 or 2 on the periodic table, except for beryllium, you can consider it neutral. Anything that came from a strong acid, also consider it neutral. So the nice thing about this is if you had, in theory, a solution of sodium chloride, it should yield you a pH of 7 in that case. Any questions on that salt? Now, obviously, not all salts are neutral. There are some salts that are basic, and salts derived from a strong base and a weak acid are ones that will actually go through hydrolysis. So for example, let's say we had a salt like sodium acetate here. So this is sodium acetate. This is a salt. And because it's a salt, it pretty much, when it's in solution, will break apart into two things, a sodium ion and an acetate ion, right? So again, we want to think about here, where did these parts come from? And do any of these parts going to react with water? So if we take a look at what we saw earlier, which was sodium from above, the sodium ion, it's obviously the same sodium ion as we talked about up here, probably means that it came from, like we talked about as well, sodium hydroxide. And what that means in terms of the sodium is it's essentially going to be neutral. It is not going to go through hydrolysis. It's not going to react with water. It's basically going to be a pH 7, not the sodium part. But what about the acetate part? Well, again, if we kind of think about the sodium acetate as where did it come from originally, it most likely came from a reaction of acetic acid and sodium hydroxide. Is most likely, again, where this salt originated from, which would produce water and sodium acetate. Well, we already identified the sodium hydroxide as being strong, which is why the sodium part is not going to do anything. But what about this guy? This guy right here is a weak acid. So this guy's a weak acid, which means its partner on the other side would be strong, and its partner on the other side would be the acetate part. So out of this sodium acetate, it is the acetate part here that will be relatively strong because it came from a weak acid. So again, that's where that sort of opposite relationship is really important. So what does that mean? Well, it means that the acetate part of the sodium acetate will decide it wants to continue to react. And what is it going to react with? Well, it's going to react with water, basically, because that's the two things that are in that solution at this point. So the water here, and what is sometimes referred to again as a hydrolysis problem. So this guy will go through hydrolysis. Now, this is also the key here is what's going to happen when it reacts with water. So understanding sort of where it came from can definitely help you sort of figure out what it's going to do. Since it came from a weak acid, that means its partner here would technically be a base, right? That's basically where it came from. So it came from an acid, which means it's like the conjugate base, which means when it reacts with water here, it's going to act as a base. What does that mean? A base is something that will accept an H+. When it does, we will end up with acetic acid plus some hydroxide. So what do we see here? Well, we see a couple of things that always sort of happen. We see that what we made is actually where it came from. So again, this is why sort of understanding these relationships are helpful, because it will allow you to write these formulas or these equations correctly. The other more important thing in terms of pH that we see is we produced hydroxide, which at that point, when we produce hydroxide, without even picking up our calculator to do an actual calculation and simply being able to write this equation correctly, we should probably 100% know when we do the calculation, this solution should be basic. And it should be basic because you are producing, obviously, hydroxide. What else is really important here is what we talked about with the idea of, should I use a Ka value? Should I use a Kb value? And hopefully you will also know at this point is I see hydroxide here, which means I should be using a Kb value when I am doing this calculation. Any questions on that? Now, this these type of problems, these salt problems, these hydrolysis problems, are the problems I was talking about earlier, where it is very, very common that they will give you the wrong K value. So in a problem like this, if you are asked to calculate the pH of a sodium acetate solution, they most likely will give you the Ka value for acetic acid. And what that tells you is you need to make sure you write it correctly. You will have to use that Kw relationship to convert it to a Kb value if you want to get the right answer. So when a salt really comes from sort of a weak acid and a strong base, it will go through hydrolysis, which means part of the salt, in this case, the acetate part of the salt, will react with water, and in this case, produce hydroxide, resulting in a basic solution occurring. Any questions on that? Well, we covered neutral salts, we covered basic salts. I'm sure you got to imagine there's acidic salts. So let's talk a little bit about the acidic salts. Now, acidic salts are derived from a strong acid and a weak base. So, for example, let's take something like ammonium chloride, which is a salt. When we have ammonium chloride, basically it will break apart into two things, NH4 plus and Cl minus. And again, this is our salt. So what we want to do is really analyze both parts of the salt here and really try to think about, will any of those guys react with water? So let's just knock off the one that we should kind of know right off the bat is not going to do anything, and that is chloride. And chloride comes from basically hydrochloric acid, right? That's really where that comes from, hydrochloric acid. And by the way, the NH4 plus most likely came from NH3. This is a strong acid. This is a weak base. And when this reacts, you will get NH4Cl as a result of it. And that is where the salt came from. So we could eliminate the chloride because really it came from this part. That leaves us really the NH4 plus. And the NH4 plus came from a weak base. And again, that relationship, as we talked about earlier, if it comes from a weak base, its partner will be relatively strong, which means in this particular case, the NH4 plus will be strong and it will go through hydrolysis. So this part here, which is really this part, will go through hydrolysis because of where it came from. Again, understanding that it came from a weak base will tell you that NH4 plus, when it reacts with water in this hydrolysis reaction, because it came from a weak base, it will basically be an acid, which means it's going to donate its H plus over. And just like we saw last time, surprisingly enough, it will make NH3, which is where it comes from, right? So again, in these reactions, it will always make sort of where it came from. The other important thing that it does is it will produce H3O plus in this case. Why is that important? Well, H3O plus, as soon as you see that, and again, without even doing a calculation, should tell you that this is going to be acidic solution. Also, much like the last one, by seeing the H3O plus here on our product side, tells us when we're doing the calculation, we should be using a Ka value. So again, there's a lot of really important information in these type of problems, a lot of stuff that, is sort of given to you, but the importance of understanding how to write these reactions are really, really important in this part of the class, obviously. Any questions on that? This would also be, again, a situation where you would probably be given in a problem like this, the Kb value for NH3. And again, you would have to use that Kw equals Ka times Kb to get yourself to the Ka value by rearranging. So again, very common, these hydrolysis problems, you need to do that. Any questions on that there? There's also another way that we could kind of get an acidic salt solution. It's kind of right here. And that is very small metals with positive charges. Typically will have acidic outcomes. So for example, if we have aluminum here, and I'll do my really bad drawing here, we'll just kind of put the aluminum in the middle. And basically attached to the aluminum is 6 water molecules attached to the oxygen, probably 1, 2, 3, 4, 5. And I'll just draw this water out. And what happens in this situation, since water is neutral, it still has an overall +3 charge because of that. What happens is another water, just a plain old water by itself, is going to come along. And what's going to happen in this case is the H from one of these waters here will donate over here to this water. And the result of that is you will produce H3O plus, which is H plus basically. And what's left over here is, again, if you're wondering how you get to this scary formula here, and I won't scare you even more by telling you later on in the semester, you'll actually know how to properly name that scary formula. But what's happening here, if we just kind of keep track of everything, we have 1, 2, 3, 4, 5 waters still intact, which is why this is here. We have 1 water that has lost an H and leaves it as a OH, which is where this comes from. And then obviously we have the aluminum there in the center. And what happens with the charge? Well, we lost 1 H plus that came off. So we become 1 more negative, which is where the 2 comes from. So basically it's a scary looking thing, but it basically is the same guy we started with, just lost an H plus as well. But this is a very common way that a small metal with a positive charge can produce H3O plus. And because it produces H3O plus, same deal here, we would expect it to be acidic. Any questions on that there? Okay. So let's take a look at some problems here involving salts and hydrolysis. So take a moment here and try to figure out what the pH of a 0.45 molar solution of KCl should be. So if we have a KCl solution, and again, it's a salt, what we really want to think about is, what does this break apart into? So it breaks apart into K plus and Cl minus. So we want to think about, will any part of this salt basically go on and react with water, right? It's basically what we're looking at. So if we look at this, what we see is K plus, which is group 1 on the periodic table. And because it's group 1, that means that this guy is going to be neutral. Why is it neutral? Because it probably came from like KOH, which is a strong base, which means it will be relatively weak. Cl minus, we've seen a couple of times, also will be neutral and not go through hydrolysis. And that's because it also came from a strong acid in this case. Probably HCl is where that came from. So because neither part of the salt will basically go through hydrolysis, we don't actually do a calculation here. The pH here should be 7. Any questions on that particular one? All right, well, of course, they're not all going to be that easy. So let's go through this one here together and think about, what happens when something will actually occur in terms of hydrolysis. Let's take a look at a salt like sodium fluoride here. That is our salt. Again, when it breaks apart, we're going to get Na plus and F minus. So again, we want to sort of analyze, will any part of this go through hydrolysis? We have our sodium, which is group 1. Again, going to be neutral, as we've talked about, because it most likely came from sodium hydroxide, right? which is a strong base. What about F minus? Well, F minus comes from a weak acid. How do I know it comes from a weak acid? Well, this is where it's really important to read the whole problem. And if we read the whole problem, it says the Ka value of HF is 7.2 times 10 to the minus 4. So what does that mean? Well, I see here Ka value. I automatically think to myself, that's a weak acid, right? And what is the weak acid? It is HF. Now, HF is not F minus, right? But if we think about this acid plus, say, that strong base, we will get water and sodium fluoride here. That is the same salt that we're actually dealing with. Again, we've eliminated sodium because of this. So now we want to really compare these two guys. Since this is a weak acid where it came from, this is going to be relatively strong and will go through hydrolysis. Again, just the F minus part. Any questions on that? So this is also why it's really important to look at the problem. There is a lot of really good pieces of information in there that can help you do this. The other good piece of information is I now know that my F minus is going to react with water. And how is it going to react? Well, again, understanding that it came from a weak acid means that the F minus here should be like the conjugate base, which means it's going to act as a base in this case and accept the H plus. Mind you, common sense tells you that it does not have an H to give, so it cannot give it, but that's a good way to remember it anyways. When it does, just like we saw earlier, it actually will make where it came from. Also, if you run into problem on these situations or questions, that's right there in the actual problem. It actually tells you what it's going to make. So that actually will give you the product side of the reaction just by looking at that. And it will produce hydroxide when it does that. And again, before even like picking up the calculator to do the calculation here, because this produced hydroxide, we should definitely know that this solution should end up being basic. Any questions on that so far? Now, what do we do? Well, we're going to do an ice table, of course. So we're going to start with the 0.3. This is going to be 0 and 0. Again, it's 0.3 molar because it's a 1-to-1 relationship between sodium and fluoride. Change is going to be minus X plus X plus X, which means at equilibrium 0.3 minus X, X and X. Any questions on the ice table? So kind of a regular, I want to say run-of-the-mill ice table, but sort of a straightforward one here. At this point, just like before, we're going to take this and put this into our K expression, which is HF times OH minus is divided by F minus. What is the other really important thing here? Well, because it produced hydroxide, because I know it's basic, this is actually a Kb value that I need here, not a Ka value. And as I mentioned before, in these type of problems, it is very common that they will give you kind of the wrong K value, right? Here they gave us this, which is a Ka value, but here we do need a Kb value. So as I mentioned before, these are again the types of problems where you do need to convert it, and that's not hard to do. We will use our Kw relationship. The Kw equals Ka times Kb. So looking for our Kb value in this case, 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4. And if we do that, we end up with, we'll call it 1.4 to the minus 11. And that is the number that we should be using here, not the Ka value. And that is a very, very common mistake that people do. They will go in with the Ka value here. So again, coming back to the idea of being able to properly write these equations and knowing what you should be dealing with, very, very important. So here, since that is obviously a very small value of K, we could assume X is equal to 0. That is going to give us X squared divided by 0.3 equals 1.4 times 10 to the minus 11. We're going to multiply to the other side and then divide. I'm not divide, then take the square root. So 0.3, square root it. Going to end up with a value of, we'll call it X is equal to 2.0 times 10 to the minus 6. We do want to check it, so we're going to divide by 0.3 times it by 100, and we are good. We're not even 1%. And again, in a lot of cases, you will be pretty good on this, so the check is good here. So what does that mean? Also important, writing this correctly, X in this case is not the H plus concentration, but this would equal the concentration of the OH minus. That means our POH would be minus the log of 2 times 10 to the minus 6. Going to give us roughly a POH of not that 5 points, we'll call it 6.9. Again, not the pH value. pH then would be 14 minus our 5.69, giving us an 8.31 for the pH. That is basic, which matches our basic prediction based on the OH minus that is there. Any questions on that there? So really important, these sort of hydrolysis problems, that you understand sort of what's going on so that you could do the math correctly. There's a lot of places where, you know, it could kind of go bad if you're not really paying attention. The other thing is, I can't tell you how many times people sort of overlook the information in the actual question. So a lot of times these questions will give you a lot of help or information about how to do it. Again, people do struggle with what comes on, say, this side of the equation. And again, you know, it's kind of given to you here in the problem. So, you know, there's a lot of helpful things, just don't kind of blow right by that information. Any questions on that there? Okay, so we got a little taste here of salts and some calculations with salts. We will actually stop right now for lecture, and we'll pick it back up next time, continue on with salts and some polyprotic acids, I think, as well.